Hello everybody, it's really nice to see so many of you here. I've probably overpromised with this, how to teach primary computing, the whole thing in about 45 minutes or so. We'll try and get you out of here by about 2:15. We'll see how it goes. What I'm going to do is talk a little about some of the sort of emerging models of practice that we can have based on theory in terms of what makes for good practice in terms of primary education. Then have a look at some of the evidence-informed practice. Precious little of that around computing, but there is some of that in terms of primary education in more general terms. Share with you some of Ofsted's expectations, and then with a little bit of luck, there'll be time at the end to talk about computing across the curriculum, just as we used to have ICT across the curriculum in the old days. For those of you who've never met me before, hi, I'm Miles. For those of you who have met me before, I'm still Miles, I really am. My day job is teaching the next generation of outstanding teachers at the University of Roehampton. Any Roehampton alumni in the room? Good to have you here. Happy learners? That's a relief. Okay. They let me out to do other things. I was part of the panel that drafted the new computing program study. Blame me or thank me, we can talk about that as well. But this is moving on from that. We've got a curriculum, we know what we're supposed to teach. The really interesting question is now, how do we go about doing that? And I suppose we look back at how things were going back in the old days. So when Ofsted last visited schools and looked at ICT education, actually, by and large, as primary practitioners, we're doing a pretty good job of that. So the teaching of ICT, good or outstanding, in nearly 2/3 of the primary schools visited. Any secondary colleagues in the room? I'm not going to draw your attention to the last sentence on that slide. That's for another presentation, I'm sure. So with the computing curriculum, we have these three elements to it. The computer science, the information technology, and the digital literacy. I see those in terms of the foundations of the subject. Its applications to getting useful things done, and then the implications of this for us as individuals, and indeed for us as a society. Take Google search as a good example of that. Anybody in the room not using Google as their search engine of choice? That's interesting, isn't it? If they were to use their powers for evil rather than good, we'd all be in an awful lot of trouble if they're controlling all of our access to information. How does Google work is a really interesting question. Well, you type it in and you can click the button. That's old school IT, and that's really important. Being able to use search well, effectively, efficiently, really does matter. But how does Google work is also an interesting computer science question about PageRank algorithms and web crawlers making copies of pages and caching those and indexing those. How does Google work is also a digital literacy question. But how does Google manage to do all of this for all of us for free is a really interesting question we ought to get children thinking about. What profile do they build up for each of us as individuals? When I talk about teaching computing, I do mean teaching all of the elements of that. And of course, the middle tier, the applications, we've got really good at over the years. The new bit at the top there, the foundations, the computer science, that's probably where our models of pedagogy may need to evolve. But what is it in that bit that we're actually teaching children? Is it teaching them the fundamental foundational ideas of computer science? Anybody else in the room know what lambda calculus is? Keep it that way, that's absolutely fine. Or are we teaching them about how software gets written? This process of software engineering, you come up with a list of requirements, and then you implement that as a specification, or implement that as code, and then maintain and test that. That's important. But we can actually leave that mainly to secondary school, I think, although there's a really interesting iterative cycle there. Or are we, as the program study suggests, seeking to equip our pupils with the ideas of computational thinking, of looking at problems in such a way that we can get a computer to help us solve them? Or actually, are we really wanting to, roll our sleeves up, treat this a little like design and technology, and make something, the craft of coding? I don't think these are incompatible things, and I'm on record as saying that actually through programming, through writing code is the best way for primary school children to develop an understanding of computer science. Don't say to me, Miles, where's your evidence of that? Okay, but the focus of where you put your attention here, what it is you're trying to achieve, might well colour your pedagogy. So, teacher trainee, University of Roehampton, you wouldn't expect to leave the room at 2:15 without me having mentioned educational theory. So let's get that over and done with now. Firstly, we learn through play, we learn through experiment, we learn through tinkering. Isn't that right, Emma? Absolutely, says Emma from King Alfred's College, Winchester. We have here 19th century German kindergarten. Look at this lovely, rich learning environment. Look at all the opportunities for the child to learn in this environment. Would it pass its EYFS inspection these days? I don't know. Although the adult-child ratio might be about right, there doesn't seem to be much directed activity happening, but who's to say there isn't a huge amount of learning happening in that space? Does this mean returning to the days of Plowden 1967? Those of you who are taking the iPad photos, all of the slides are online. I'll give you the link at the end if you don't want to keep photographing each slide. It's fine. It is. So the Plowden report about putting the child at the centre of education. But Nick Gibb, I'm sure, would tell us that was a fad and we've grown out of that now. But actually, hand on heart, shouldn't the child be at the heart of what we're trying to do as a primary school? Shouldn't it be about meeting children where they are and taking them on to someplace they wouldn't have got otherwise? And look at that last bit. The main educational task of the primary school is to build on and strengthen children's intrinsic interests in learning and lead them to learn for us themselves. Why is that not an aim of the national curriculum? Learning to learn, a love of learning. If your school isn't trying to do that, then I'd love to know what it is you're setting out to do. Of course, this has got to be part and parcel of what we do. So providing children with the toys to play with, the blue bots, the bee bots, the scratch, the Odoo, to learn this through play. And those who get jobs in the industry, your Zuckerbergs, your Gateses, your jobs of the future, are folk who've learnt this for themselves, who've self-taught very often, not always. And I think I go back to Pappert's vision for computing education way, way back, 1980, 1991, when he wrote this, that the best way to learn, particularly in this domain, is through making things to show to others. That it's art. Computing education ought to be a creative domain of knowledge. It has things so much in common with art and design, with music, with design and technology. The best ICT lessons, I think the best computing lessons, are those where we make something, making the scratch game, making the coding game. You learn so much through that process of making things to show to others. Not just the craft skills of coding, but also that understanding of how the technology works. And of course, we'd also make reference to Vygotsky and the power of language, not just to learn from our own experience, but to learn from others' experience, providing those opportunities in your computing lessons for children to ask one another questions. Do you have that experience in computing lessons of, Miss, Sir, can you help me do this, please? Send them back. Don't let them ask you until they've asked one another. Now, I have trainees coming back from placement and said computing lessons they weren't allowed to talk to one another. What a wasted opportunity. So much of this happens through sharing ideas from one another. Software gets developed through a collaborative process of people working in teams to get something done. That's how it works. That's how it works in the real world. Slide here. This is a multinational technology firm's office. This doesn't look like a call centre. Compare and contrast with your school computer lab / IT room or whatever. Okay, but we don't have to limit those conversations to what happens in the room with us. This wonderful network of interconnected computers that have been around for a little while now allows your pupils to continue those conversations, to learn from the experience of others elsewhere on the internet, elsewhere on the web. And I know there are e-safety issues, but try to find some way of managing those concerns, of allowing children to use the power of the internet productively, effectively, so that they can connect to and collaborate with others online. It's access to information and being able to work collaboratively, being able to connect to the ideas that are already out there that lies at the heart of this. Scratch, great example. Yes, the building blocks in Scratch are fabulous. But the most fabulous bit on the whole Scratch interface is that little share button up at the top of the screen, allowing children to get that global audience for their project, allowing them to remix the things that others have done, allowing them to comment on one another's projects. Of course you need reasonably broad shoulders. I have Scratch projects on the Scratch website where I've had 8-year-olds saying it's not very good. Is it? You've not been doing Scratch for very long, have you? I have broad shoulders, I can cope. Developing a certain resilience amongst your pupils may not be a bad thing, though. Okay, controversial bit coming up. Once in a while, it may well be the most effective thing you can do is to actually teach them something. Yes, provide the opportunities for them to explore, provide them the opportunities for them to make something, but once in a while there are ideas which they may not figure out for themselves. And us swapping into a slightly more didactic mode and saying, okay class, I'm now going to explain something to you, may well be an efficient and effective method of crossing some of this territory. There's this notion of the threshold concepts, the ideas that you wouldn't figure out for yourselves just through play, exploration and discovery. The things that once somebody takes the trouble to explain that to you, your way of thinking about the world, or at least thinking about computer programming or technology, changes as a result. I put abstraction on this list. Once you see the idea of abstraction, that is managing complexity, that is layers of complexity, of black boxes inside other black boxes inside other black boxes, your way of thinking about programming, your way of thinking about technology changes as a result. There are, I'm sure, others on that list. We might add into that things like, I don't know, the variable in Key Stage 2. Will children figure that out for themselves through playing Kodu, through playing on Scratch? Perhaps. But actually, once in a while, explaining that may well be the best, most effective way to do things. And actually, practicing these skills. You know, I still see a good outstanding lesson as one in which children come away knowing more, understanding more than they did when they went in. But that's not to say there isn't a place for consolidating the skills, the knowledge, the understanding that they already have. Just because you've taught it once doesn't mean to say they've learnt it. So providing the opportunities for spaced repetition, for them to have another go at this idea, make the connections for them, yeah? Say this is the idea of abstraction in practice, or we're going to look at an algorithm and we're going to look at translating that into code so that the computer can follow that. So providing the opportunities for them to practice these skills. Teaching it once may not be enough. And of course, when it comes to coding, the opportunity to learn from your mistakes. If any of you have read Carol Dweck's work on growth mindsets, you'll know how important a child's attitude to their mistakes really is. And you know, when you make mistakes in maths, being told to go and do your corrections, it's not particularly motivating, it's not the most exciting bit of maths education. But in computing, you get the feedback straight away from the machine. It either compiles, or it runs, or it doesn't. And so many children are at least willing to have a go at finding their mistakes. If again, you've got, Miss, my program doesn't work, can you fix it for me? I'd say your default position on that should be no. It's not my job to fix your code, it's my job to teach you. Fixing your code is an essential part of learning to be a computer programmer. And in computer programming, you do learn from our mistakes. And yes, that will be frustrating. Yes, that will be hard. But live with the hard, live with the frustrating. We have reasonably robust evidence that when they find it easy, they're not learning very much. It's only when they have to engage their brain and meet something that's challenging that the best learning takes place, I reckon. So do we have evidence for what works? Well, precious little when it comes to computing education, and there is a task for us as a community of practice here to get that evidence, to start doing the investigations. Is it true that it's more effective to teach computer science, to teach computing through practical hands-on experience? Could you provide me with some evidence of that? Let's split the class, the year group, into two groups. One group we're going to go unplugged, the other group we're going to go so plugged. We're going to give them Scratch, we're going to give them Kodu, we're going to give them iPads to code on, and let's see at the end which group is better at computational thinking. Let's see at the end which group is better at computer science and their understanding of computer science. Radical idea? It would be nice to have the evidence so that we know what's effective practice. Okay, there is limited evidence, but we're starting to see emerging evidence of good practice. John Hattie, brilliant book, Visible Learning, get it if you've not got it already, goes into your staff and should be on your professional development library. He's looked at 800 academic meta-analyses of proper randomized control trial, impact-based studies of what works in practice, and summarizes that whole body of evidence in the one sentence on the screen behind me. The biggest effects on student learning occurs when, wait for it, teachers become learners of their own teaching, and when students become their own teachers. And he's got the evidence to support that view. When you get better and better at doing what you do, we become, I'm one of them too, a reflective on our practice, reflective practitioners. But passing on some of the responsibility for learning to your pupils themselves. That is not your job that they learn. It's your job that to teach them. And they should be taking some of that responsibility for learning themselves. And that seems to have a big impact from Hattie's point of view. He doesn't talk about computing education in detail, but he does talk about using computers in education, in teaching and learning. And his evidence, or the meta-analyses on which he draws, says it's most effective when, wait for it, folks, you'll be surprised by these, there's a diversity of teaching strategies. So that first half, that's not a menu for you to choose from. The idea is it's a toolkit where you draw on all of those strategies in a very pragmatic way. What will work for my subject with my students on this occasion? And wait for it, there is teacher pre-training in the use of computers as a teaching and learning tool. Radical observation that, so glad that he's put all of that evidence together, that it seems to work better when teachers know what they're doing with the technology. Does that ring true with your own practice? Hope possibly. Okay. Other things there as well. Multiple opportunities for learning. Don't just do it in the once. And this next one is really interesting. The student and not the teacher is in control of their learning. Come back to that fad of child-centered education. Come back to the kindergarten approach, giving children some autonomy, some independence in what it is that they're doing, what it is they are learning. Seems to be quite effective when there are computers involved, possibly because of the quick feedback loop that you get there. Peer learning is optimized, providing all of the opportunities for children to teach one another these ideas. Remember my Vygotsky stuff about language as the medium for learning in your computing lessons. And of course, it's really, really cheap. Children work for less than the minimum wage. And also you're giving them feedback, but in computing, the machine is giving them feedback. That, I think, is why it's different from many, many topics. Certainly from ICT, where you have to, the old school applications bit of IT, where you had to say, yes, that's a really good PowerPoint presentation, well done. In computer science, in programming, the computer will tell them whether it works or not. They'll see whether it does what you need, what it's supposed to do. So feedback being optimized, I think, does work. If you've not seen it already, this is your go-to toolkit for what works in education. Education Endowment Foundation's toolkit. The idea is, what should you spend your pupil premium money on? And some radical discoveries there that apparently the most impact you can get is through giving children feedback on their work. And that makes 8 months difference compared to not doing it. I love the notion of the randomized controlled trial study where one class didn't have their books marked for a whole year and we saw what difference that made. But it does seem to make some difference, giving children feedback. And remember my observation that in computer science and programming, you're getting feedback from the machine as well. Metacognition, self-regulation, learning about learning, thinking about thinking, getting children to take that responsibility for their own learning. I know I'm repeating things, occupational hazard in my line of work. Peer tutoring as well, getting children to support one another in their learning. Use your digital leaders. Who's got digital leaders in their school? Okay, that's not enough of you. The rest of you go home and do something about digital leaders, please. Okay, get children to take some responsibility for helping one another do these things. There are other things on the list. It's quite entertaining to click on the link on the website and see what comes bottom of the list there. Things like ability-based grouping, way, way down the list. Yes, it works for the brightest and best, but it doesn't help address the performance of the whole. And Bart Simpson puts it very, very memorably in one of the episodes where he says, so, let me get this right, we're going to catch up by working at a slower pace than they are. He has a point there, doesn't he? So think, one of the things we've done with the computing curriculum, it's entitlement for everybody. And then there's this. So Robert Coe, Professor of Education up at Durham, says discovery learning doesn't seem to be supported by the research evidence. And the Kirshner et al. Study says that actually direct instruction is the most effective way. They look at Kirshner et al. Most of their references are down to science education, and maybe they are right. But actually, I think in computer science education, many of our experience suggests that discovery may well be an effective mechanism. There's a really interesting discussion about this particular observation on the Computing in Schools site, direct instruction versus discovery methods. It is an open question, it really is. And if we had more time, let's open that out to debate. I'd be interested to hear your views on that. I really would. As I say, open question. Okay. Some of you, I'm sure, are interested in what Ofsted are expecting. Well, broadly speaking, all you have to go by What you have in terms of Ofsted's expectations is the main Ofsted inspection handbook. There's nothing else in terms of official guidance currently online on the Ofsted site. What are their expectations in terms of outstanding teaching across any subject, irrespective of what it is that you're teaching? There's nothing. No, there's one on that list, which is, I think, a little bit controversial. Having high expectations of your pupils. I hope there's nobody sat there thinking computer science is too hard for some of my pupils. That's not what the National Curriculum Entitlement is about. It is for everybody. Yes, it's challenging, but being challenging is a good thing here. That your teaching should enable exceptional learning, that when you intervene it should have impact, and you should know it has impact. That there should be high levels of commitment of engagement, that your teaching strategies should be well judged and imaginative. Remember my menu of different toolbox of different techniques you can use, and of course you should match it to individual children's needs. The one I skipped over there is the one I'm not entirely convinced about. Authoritatively impart knowledge. We apparently have an education inspectorate who say we're open to all teaching styles, there's no single preferred teaching style, we're interested in the results that it has. And yet it's a criteria for outstanding teaching that your teaching must authoritatively impart knowledge. And when I look back at what Hattie says and when I look back at what the Education Endowment Foundation say, they don't seem to be giving me evidence to say authoritatively impart knowledge has a particularly positive impact. So in computer science, is that the best way to go? Well, perhaps if you happen to have an Ofsted inspector in the room, do a little bit of authoritative imparting of knowledge. But elsewhere, perhaps discovery, play, exploration, children teaching one another may still have its place. So David Brown, who's Ofsted's National Lead for Computing and E-Safety, did a brilliant presentation at the launch of Barefoot Computing back in July and put his slides up onto SlideShare. They're covered under the terms of the Open Government License, so hence the copy of them here without the Ofsted logo. I'm not speaking on Ofsted's behalf. But then Ofsted asked him to take the slides down. So these slides aren't on Ofsted's official SlideShare site, but, they're here. Have a look at what he was expecting back then in terms of particularly computing teaching. Excellent subject knowledge, and that has been one of the things which Barefoot Computing, Quick Start Computing, and CodeClub Pro, many of the other schemes have been aiming to address, helping you fill that gap in. I never learned any of this when I was at school, but we've tried to help you with that. Excellent subject knowledge makes a difference. High level of competence and expertise, not only in terms of knowledge, but also getting the kit to work. That does seem to make a difference. Understanding of active learning in computing, that's not authoritatively imparting knowledge, well, I'm sure David Brown would disagree if Michael Wilshire were to call him to account on that. Rooted in the development of pupils' understanding of the concepts and pressure. It's not about learning Scratch. It really isn't about learning to do Scratch. It's about learning computational thinking, computer science, maybe the craft of software engineering. He says other interesting things too, addressing pupils' misconceptions. If you want to get a taste of pupils' misconceptions, ask them to draw the internet. That'll give you some idea of what their current view of how the internet works is. If they draw Stampy, which is what I had from a boy a couple of weeks ago, you may have some misconceptions. Draw Stampy is the internet? Not quite. Okay. Teachers communicate high expectations, enthusiasm and passion. Those of you who are not feeling enthusiastic or passionate about the subject, okay, you've got to work on that one. You probably aren't at this bit of the BETT show either. Innovative and imaginative resources. I'm going through his bullet points, which is not the most exciting way of doing this sort of thing. He also talks about a good computing curriculum. And okay, we've done that in terms of national curriculum, but look at what he's expecting in terms of your planning in school. Second bullet point is really, really important here. The curriculum is broad and balanced within all three strands, and all three are covered well in computing lessons and across the school curriculum. If all you're doing in computing lessons these days is coding, then you're missing out on that. It's still information technology, there's still really important digital literacy that you need to cover. Again, if you're still just find things out on the internet, make a presentation about it, you might want to get up to speed with some of the computer science programming things which we've been introducing recently. Look at the way to make links to other areas of the curriculum. Look at the way to involve other agencies. Look at the links with your local industry. You'll all have parents or probably governors who work in the industry. Get them to share some of their expertise. Much of this is related to secondary, but notice the bullet point there about e-safety. Notice about realistic and challenging situations. Learning to program just so you can learn to program isn't, I think, what David would mean, or certainly not what I would mean, by realistic and challenging situations. Really interesting bullet point at the bottom there. Inspectors are aware that this year, Year 7 can't, if you're teaching Year 7, you can't assume that pupils have covered the whole of Key Stage 1 and 2 of the computing curriculum. Ditto, if you're teaching Year 6 this year, trying to cover the whole of the Key Stage 2 programme of study within Year 6, plus you've also got the SATs to do, good luck with that, but Ofsted appear to understand that that might not be an entirely reasonable expectation. Next year may be another matter, of course. Just want to draw your attention to one bullet point on this slide, again from David. Pupils, second bullet point down, that it's inadequate. I do feel sorry for the schools who get their photos displayed on the slides where it says inadequate at the top. You know, Ofsted say, can we use your photographs on our slides? Oh, yes, of course. And then you find it's labelled on the slide for inadequate. Never mind. Pupils rarely demonstrate creativity or originality in their use of computing and seem confined to following instructions. That's inadequate teaching in David's book, and I think in our book too. Could you please type this into the computer, type that into the computer, type that into the computer? What you're doing then is not teaching programming, you're programming children. Giving them a sequence of instructions to follow is treating them like computers. They need to bring their originality and problem-solving skills to the party. Of course they do. Yes, there's a place for learning to use user interfaces, of course there is. But you can't simply give them things to type in and expect them to learn that way. Just one or two bullet points in terms of leadership in computing, because that third bullet point is really very interesting. Access to computing equipment is outstanding. That really does seem to matter. And that the school is likely to have promoted the use of mobile technologies. So bring your own approaches, making some reference to mobile technologies, not necessarily buying an iPad or other tablet-based device for every child in the school, but some recognition that many children will have that sort of technology and bringing that into the curriculum, maybe bringing that into school. Anybody else remember being allowed to bring in games for the last day of term? Okay, even if you're not in a bring your own device or bring your own approach school, why not one day a year? Let them bring in their phone, let them bring in their pad. Anybody here got the ICT mark? Okay, well done. Okay, it's well worth going through the NACE self-review framework for this, but again, their expectations in terms of teaching to get that particular stamp on your letterhead enables pupils to use and develop all aspects of their computing capability through a wide range of experiences and context, matched to their needs, abilities, and learning preferences. More child-centeredness, mumbo-jumbos would say Nick Gibb, or Thad would say Nick Gibb. Okay, how are we doing time? So, yeah, have a look at the way software gets written out in the real world. Sorry, real world, the industry. Schools are part of the real world too. I think there are some really interesting lessons which we can bring into our line of work too. I think one of those is this notion of teaching as a craft. What we do is much, much closer to architecture than it is to sculpture. I say to my trainees, what's the difference between architecture and sculpture? And they look at me with a slightly worried rabbit-in-headlight view. I think it's because they think the question is a trivial one. Let me explain. The difference between architecture and sculpture is with architecture you've got to live in it or you've got to work in it. With sculpture you can just say that's beautiful. What we do is closer to architecture. We've got to build something which is useful for our pupils. Just doing something which is interesting, which we think, oh, that was such an engaging lesson, isn't enough. It's got to be something which is useful for them. It adds value to their lives, I suppose. Back in the old days of software development, they have this thing called the waterfall development methodology. Anybody who happens to be teaching A-level will be all too familiar with this, because we still teach this on the A-level specifications. How's that for moving with the times? With waterfall development methodology, you start by somebody in a really nice office says, our software should do this, or every child should learn to code, or things along those lines. Then other people have the job of designing a way of it doing that. They tend to have, fairly nice offices. Over in the computing curriculum or curriculum development world, I was part of the panel that drew up the computing curriculum. But then we give to other people, programmers or in our line of work, I don't know, teachers, the job of implementing that. They tend not to have much say in the requirements or the design of the specifications significantly. In software development, they do loads and loads of testing. They need to make sure that what they do works. In our line of work, we do a fair amount of testing too. We also, of course, need to occasionally maintain the thing that we produce, and there may well be a case of stepping back. Is this working? How do we tweak this? How do we improve this? It will get better and better. This year is a minimum viable product. Now, we know this works incredibly well for big, wide-scale public sector software projects like the NHS database. So it's bound to work well for curriculum development too. Okay, and then you have Nick mentioned him already today, saying this. Counted as a success when teachers are able to laminate their lesson plans and recycle them from September to September. I hope you're all laminating your lesson plans this year, be able to use them again next year. Not happy about that? Because it's a different class, Miles, and because I've not yet taught the perfect lesson. When I teach the perfect lesson, that's the lesson plan I'm happy to laminate, but not until then. So perhaps you'll be familiar with this cycle from your teacher training days, I'm sure. We have an iterative approach to this. We plan our lessons. Oh yes, we do plan our lessons. We teach it and then we do our assessment. Have they learnt what I should have taught? And then hopefully it feeds back into a loop of I could have taught this bit better. I could improve on this. And that improves the way we teach. And the same thing, same cycle applies in software development. Yes, we design the program. We code it, we test whether it works, but then we evaluate it and then come back and think of, yeah, there are these bugs, there are these features to add. So I think there's a strong parallel between iterative development and our planning, teaching, assessment cycle. But the software industry has moved on. The software industry says, yeah, the things on the left do matter, but actually the things on the right, this is called Agile development, matter even more. And I think in our line of work, who was it in here who came into the profession because they loved writing lesson plans? Hands up, please. Okay, because they loved working with children? Once upon a time. Yeah. So that, we do it because of the individuals and interactions, not because we like writing lesson plans. And why do we spend so, abstraction is about managing complexity, yeah? Why do we spend so much of our time focused on things on the left there? About planning and documentation, processes, tools, and not nearly enough about the children who happen to be in front of us and our interactions with them and collaborating with them and being responsive to the things that they suggest. And they say, this, sir, I'd like to learn about. Shouldn't we be responsive enough? With the trainees at Roehampton, if I'm supervising a trainee out in school and they just stick religiously to their lesson plan, it's hard to see that as outstanding teaching when something happens in the room which suggests, yeah, I've got to adapt, I've got to be flexible here. Interestingly, software development, we can move on beyond Agile into this territory of craftsmanship. I think for us, this is a really interesting territory. So yes, the stuff on the left is great and why we come into teaching, but actually the stuff on the right is even better. It's not enough just to teach an interesting and effective, exciting lesson. It's got to be an effective lesson. It's got to be one where the children learn something. And yes, collaborating with our pupils matters, but also developing partnerships with others that are really productive. And yes, working knowledge matters, but having the best possible lesson, being proud of what we do. And yes, remember the children that you're working with, but don't forget this wider community of professionals of which you're part. So, yeah, that matters. Okay, we've got enough time. Let me just touch on one or two aspects of cross-curricular computing here. So, we start with this. This is the opening sentence of program study. High-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. I think the task for Ofsted is easy. You just go into primary school and pick a child at random, say to them, have you understood the world? Have you changed the world? Tick in both boxes, job done. Okay, really. This is a pairwise thing, though. Computational thinking to understand the world and creativity to change the world. You notice it's not about coding. Coding is the means to the end, not the end in itself. And the computational thinking thing is something which we can develop across the curriculum. The Barefoot resources are fabulous on this. And what we've done at Barefoot, based on some of Julia Briggs' work in Somerset, is to say, yes, there are a whole host of concepts which you draw on when thinking about problems in such a way that a computer can help us with them. We have logical reasoning, we have algorithms, we have that step-by-step approach. We can break things down into their smaller parts and deal with each of those separately. We have patterns. A good computer scientist is a lazy computer scientist, looks for other ways of doing these things. We manage complexity through abstraction, and yes, we do make judgments about whether what we do is effective. None of that needs to work just with code, though. All of that is something which you can do across the curriculum. Getting children to spot flaws in logical arguments, isn't that a really important use of logical reasoning? Getting them to think, that doesn't follow from those premises. This should be critical in their thinking around that. Getting children to think about the steps to get other things done than just write computer games. How do we get ready for lunch? How do we make pizza? Getting children to look at big problems and break them down to smaller parts. Mind mapping, research projects, putting on a play. Let's put on a play. All of that, we break it down into smaller parts. Yeah. Your 3-part lesson is a pattern we fall into, I think, possibly a little too often. And so much of school life is about managing complexity. Your timetable doesn't capture what's happening in every lesson. That's down to, actually, it's not even your lesson plan, it's actually, the rich, nuanced, how it actually happens there in the room. But Barefoot also says, as well as those concepts in computational thinking, there's a whole cluster of approaches there. And much of those relate to what I was saying right at the beginning of the presentation. That thinking like a computer scientist, thinking about getting the computer to help us solve problems is about play, is about being creative, is about fixing things when they go wrong, is about sticking out things when they're hard, and it's about working with other people. So, coders or computer scientists, computational thinkers or programmers, architects or bricklayers, which do we want our pupils to be? I think my answer would be both. Being an architect without being a bricklayer, that's fine and dandy, of course it is. But being a computer scientist, being a computational thinker without the experience of writing the code, that seems such a shame. It's going to be so difficult to motivate children, I think, to do that well. But then again, being a coder without doing any of the computational thinking, that's kind of missing the point there too. So for me, programming is a 2-step process. It's how are you going to solve the problem and then implementing that as code on the particular digital device that you have in front of you. It's taking the ideas, which is where the really creative work is, and then applying your technical knowledge of the particular computer system to make that happen on the computer. The computer is the extension of your brain. Once you know how to solve the problem, you can get the computer to do that for you. So why do we teach programming? Because it seems to be the best way for primary pupils to learn about computer science. You're supposed to say at this point, Miles, where is your evidence for that? Look, there's a reference on the bottom of the slide. Berry 2013, it says so there. Not enough, not good enough, really isn't good enough. But in science education, I think we believe that the best way to teach primary science is through getting children to do experiments, getting children to plan investigations. I wonder if they have evidence of that. I've not checked. I think if I think back to my primary school days and my trainees think back to their own school days, they remember the science lessons when they did the experiments, less so the science lessons when it was all about theory, when it was all copying down notes. We try to forget those lessons. And so yes, the practical hands-on work, the craft of coding, is hugely important. How can you do this? How can you embed this computational thinking, this application of that to real-world problems across the curriculum? There's a list of, is that 9 things up on the screen behind me, not all of which are going to involve programming computers, but some of them certainly will. The whole thing about phonics, isn't that what text-to-speech and speech-to-text engines do? How do you program an iPhone? How do you program a computer to be able to listen to what somebody's saying and convert that into text? Isn't that what a child does when they start learning to spell, learning to write? How do you teach a program to read out loud a text to you? Oh, it's well worth going onto sites like Voki and swapping the language set over. So take the text, but apply another language's grapheme-phoneme correspondence rules to see that in action. And okay, learning about HTML not specified on the national curriculum is so important, so useful. Isn't that a great way into thinking about how to structure a document when it comes to some things in Key Stage 2 English? Over in Key Stage 2 Mathematics, children should learn to tell the time on the 12-hour clock using Roman numerals for their face marking, because that's so relevant in the third millennium, isn't it? Okay, but why not get children to make a clock? Making a clock over in design and technology, that'll keep them busy like all year or something. Over here in computing, we can do that in Scratch. It's a lovely Scratch project, by the way, because you first need to make the clock mechanism, the thing that goes tick, 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 tick every second. Then you do the user interface of, can I display it on a 12-hour hand, or can I use digital numbers for that? Teaching fractions to a computer. Scratch doesn't come with fractions built in. If you want to teach Scratch to add together fractions, you've got to have a really deep understanding of that algorithm before you can program the computer to do so. Programming is algorithms plus code. By thinking about the algorithm there, once they're good at coding, they'll get a far, far deeper understanding of how fractions arithmetic works. There are other examples up on the screen now. Oh yeah, history curriculum has a topic after 1066, looking at the chronology of that. Why not do history of communication? Science Museum, Information Age Gallery, absolutely fabulous. Berners-Lee, Turing, I suppose you've got Babbage as well, the Telegraph, so much of this is there. And what a lovely topic to look at the history of. Last thing, it works better when you click on the link on the slides. Here are 6 Scratch projects I've done to illustrate sort of ideas across the curriculum. Here is the Scratch clock jockey. Here is doing frequency charts for dice simulations. This was back in the day when probability was on the maths curriculum. Make your own solar system in Scratch. Sorry, make your own simulation of the solar system in Scratch. The other thing requires extra hardware. Then, what's that one? Get it doing phonics checks in Scratch. So get it to read out the letter. Child presses the letter, whatever, on the keyboard to show that. Lovely, lovely turtle art projects. Return to your logo programming. It is brilliant for maths, for art, and indeed for religious studies. Think about Islamic art there. And finally, modelling interesting real-world problems, showing the spread of an epidemic using Scratch as a toolkit for modelling that. Where'd you go to find out more? Come and have a chat afterwards. After this, I'm going over to the Rising Stars stand, brief plug for my publisher there. Switched on computing, better order now. So there's time for more sort of informal Q&A session over on their stand. But I also ought to mention a number of other things. So we've got the CAS, Computing in the National Curriculum, primary guidance document, which is your starting point for what does the program study mean. Over on the right-hand side, launched this Wednesday, 2 days ago, at BETT, available on the DFE stand. Quick Start Computing, CPD Toolkit for Primary Teachers, 64-page book which covers the subject knowledge of computer science, but also mentions very briefly some of the ideas about pedagogy, assessment, planning that I've touched on today. Barefoot Computing resources I've already plugged, and do join Computing in Schools. Who here is a Computing in School member? Was it worth your membership fee? Absolutely, okay, hopefully a little bit more than that. It's free to join. Do register. 17,000 members, I think doubling about every 7 months or so. At this current rate of doubling, in about 10 years' time, it will be everybody in the world. So get to the point I would suggest. Okay. These slides are online, so bit.ly BETTeachComp will get you the slide deck again. Oh my gosh. So that's all on there. There's a twittering thing, there's an email address, there's a blog, which I very, very rarely maintain. We have about 2 minutes for questions in plenary. Is there anybody who wants to say something which they think other people would like to hear the answer to? All right. Fine. Thank you ever so much for listening this afternoon. It's been lovely to meet you all, to be here with you. I'm going to hang around for a while and then I'm off to the Rising Stars stand. Thank you.